Hello and welcome to our discussion on correlation. This will be a shorter one where we just introduce the concept that we are going to focus on, and in future videos we'll look at working slowly through some examples. So we'll more do an overview here like we usually do, where everything is sort of calculated for us, and then we will just get an idea of what is correlation all about. I'll write that over here, correlation. It's essentially an investigation into whether two variables or quantities or factors are related to one another somehow. So a first example is investigating whether loneliness and depression are connected in this fictional example. So we have a rating system of each one, a loneliness rating and a depression rating. And we have our sample of 1, 2, 3, 4, 5, 6 people that were surveyed in this study, and they rated their loneliness and their depression separately like this. First, to visualize the information, we can have a little scatter plot graph here where, for example, we put loneliness on the horizontal axis, depression on the vertical axis, and then we see here this loneliness of 1, depression of 2 is that one, for example. And then we can make a dot for each of these sample values. And if we have a lot, sometimes, we might visually see that they form some sort of line. And we might say that, well, these don't seem fully random. They seem to follow a line like that somewhere, just as an initial investigation. It looks as if there might be a connection between these two. I don't know how strong the connection is. I don't know what the connection is, but I'm trying to establish if they are related in some way, and we call that correlation. So the next question then is, well, how are we going to come up with some calculated number to measure the amount of correlation, the amount of how strongly these are connected and how. So from my initial visual assessment, it looks to me personally as if the loneliness rating is higher, then it seems, I suspect, that the depression rating goes up as well, but not by as much. See, the line is fairly flat. Now, this is just my rough line. Don't know if this is true or not. Fairly flat, which means if I increase the loneliness rating a lot, the depression rating does increase, but not by as much. It's a flatter line. But I do see some connection. So how are we going to do this? Well, it's going to be a little overwhelming at first, but I'll show you all of it on the screen there. We're going to take each of these variables or factors, X, and call loneliness, for example, X, and call the depression one, for example, Y. We stick to X and Y usually. X will be my horizontal one, Y will be my vertical one. Then I could flip them around, of course. So I have all my X scores here and my Y scores. For each one, I'm going to calculate the Z-scores of that sample. So how do I do that? Well, I need to calculate the mean. I need to calculate an estimate for the mean, the sample mean, sample standard deviation, And then, of course, the z-score is, well, for x at least, is going to take my x-score and I subtract the mean, the x1, this 5, over the standard deviation, just like I've done for quite a while now. And then I get this z-score column. I'm sort of standardizing the scores, and I do the same thing for y. The benefit of having the z-score instead of the raw scores, as we've seen before, it has the benefit of standardizing it, so they're always a comparable scale, as well as it has more information in that it measures how far each score sits and which direction from the mean, how far in terms of number of standard deviation steps. So the z-scores have a lot of information in them. What we're then going to do is we're going to, for each pair of x and y values, for each person in the study, we're going to multiply the z-scores together, and then we're going to average that to get our correlation coefficient. That we are going to call R. So that is going to be the number that tells us something about that. That's how we're going to measure this correlation concept. Now, multiplying the z-scores together have a certain effect. If both the x and the y scores are high, so on the graph, maybe this guy, right? It has a high score for both. Then what is the effect of multiplying the two z-scores together? Well, they're both going to sit above their means. They're both going to be positive, and multiplying them together contributes a positive value to the correlation coefficient. If they're both low, like this one over here, then they're both going to be negative. But when I multiply them together, they're going to contribute a positive number to the correlation coefficient. So if I just look at these two, forget all the rest. Let me make it easy for you and get rid of them for a second. They're gone. They don't exist. La, 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 la. Hopefully I can undo that. They don't exist. Then if I just look at those two, there is this line that goes from the bottom left to the top right, and we're going to call that type of correlation a positive correlation, because both of these pairs of values will contribute a positive amount to the correlation coefficient. Okay, so let me just back that up like that. Whereas if I have the other extreme, like I am black here. Let's make my own dot. Make it a little more extreme. This guy over here is going to have a low x, but a high y z-score. So it's going to be low x, high y. It's over here. So one will be negative, one will be positive. And then when I multiply them together, I'm going to get a negative number. Same for the other extreme. If I, for example, have, well, I can look at this one, sure. This one over here. Same thing, I'm going to contribute a negative number to the correlation coefficient. So if I temporarily just forget all the other dots, and I think about this, oh, I should have gone right through it, but whatever. This kind of correlation, it's different from the other one. We're going to call that a negative correlation, and the correlation coefficient will be negative. Let me back that up. So if I jump ahead to examples of things one could get, I have here, you see this trend. It looks like they're associated with a positive correlation. And when I calculate the correlation coefficient, all these guys will contribute positively to that correlation coefficient. And the other ones, there aren't extreme negative correlation contributors. But I could get a layout like this, and then my correlation coefficient will be negative, corresponding to this connection between the variables. And the more I have that contributes largely to this correlation coefficient, the stronger my connection is between these variables. So this will be a strong correlation, both positive and negative, as it drifts closer to 1. But if they're a little bit more scattered, the correlation coefficient, whether it's positive or negative, will be closer to 0. That's a weaker correlation. See, the evidence doesn't suggest as strongly the connection that I saw at the top here. Yeah, there looks like something, but there's a lot of other things I'm getting as well. And then, of course, it'll be very weak in the bottom here. So regardless, the correlation coefficient is a measure of how strongly, if at all, these two variables are related to each other. So in this case, I get a correlation coefficient positive of 0.73. So we say there's a positive correlation between these two, and it is fairly strong. Let's look at, that was my slide there. Let's look at another example just to go through how it's calculated, and it's really not hard at all based on what we've done before. So here we ask, is there a relationship between the love felt towards one's partner and the amount of conflict with that partner? So I have 1, 2, 3, 4, 5, 6, 7 people that I've surveyed, fictional of course, and they rate their love and their conflict shown here. I can graph it to get an idea visually. What do I think? It looks to me like a negative correlation. I don't know how strong it is. That's why we calculate the correlation coefficient. So we have the two variables separately, calculating their z-scores. Very familiar. Go way back to the first few topics, and that's where we are getting how to do that. And then we multiply them. We call them cross products. Some of them are positive, some of them are negative. And you see here we get a negative correlation coefficient, negative 0.64. So it's not very clear here, negative. So it's definitely confirms the negative correlation that I saw there. It's not very close to 1, but it's certainly not weak. Maybe medium to strong. And of course, these classifications, when do we use the word strong, weak, medium correlation? It's a little bit subjective for sure. Let me just see what the next slide is. So just an overview for how I do this. I hope you agree at this stage in our journey. It's not super complicated. I want to change all the scores for the variables to z-scores, keeping them separate. Then the cross product for each pair, each person. And then I add them up, divide by how many there are, just a simple average, and that'll be my correlation coefficient. So how do I interpret this? Interpretation of R. Now, probably more than one way, but way that you might see come up in research papers is by way of squaring the correlation coefficient. And that is then called a couple of names. I'll call it the proportion of variance or variation. It doesn't matter. Accounted for. What does that mean? That means that if I think about the first example, what did I measure there? Loneliness versus depression. My R is 0.73. Just as an example here, 0.73. Now, of course, loneliness and depression, according to this, seem to be related to each other. But of course, they're related to other things as well. Other things could affect depression, maybe your financial situation. Other things could be affecting loneliness and therefore affecting the relationship between these two as well. If I calculate R squared, let's quickly do that. See if it wants to pop up in my Discord messages. Doesn't always, but let me calculate it. So it's 0.73 squared. We get 0.5329. This tells me, if I convert that to a percentage, 53.29% of one variable is, how should I say, what's the best words here? Let's use depression, for example. 53% of the variance in depression scores is accounted for due to loneliness. Let's say it like that. So one way that I could interpret this, of course, I can flip it around. Approximately 53.29% of the variation in depression. I'm going to run out of space here, so I'll say here depression scores is accounted for due to loneliness, let's say. Not the best explanation, not the best wording here, but you get the idea. Can I spell properly? Thank you. So other things could be affecting depression, but 53% roughly of the depression score seem to be coming from loneliness in some way. Okay, so that's a nice, good, handy interpretation of the correlation coefficient. Of course, I don't know exactly how these things are related. And there's one danger trap that we can easily fall into. Go to my slide here. Oh, let's not do that. No, here. In that, I'll write it first, and then we'll look at the slide. Correlation. My writing is just amazing right now. Does not, let's say, imply causation. What does that mean? It means that if there is a correlation between two variables, it does not mean one causes the other. It could, but it doesn't necessarily mean that. All I'm saying is that, all the evidence is saying is that there is a connection. It does not say what that connection is. For example, here's an example where we are investigating exciting activities, or the rating of how often a couple undertakes exciting activities, and then rating their marital satisfaction. It could be that exciting activities has a direct effect on marital satisfaction. It could be the other way around. If there's a correlation, marital satisfaction could cause a higher rating in exciting activities. It could be neither one of these. It could be there is a third variable that affects both of these, and through that variable we get a correlation between those two bottom variables. We don't know. So it's very tempting and dangerous to do a correlation investigation and then interpret that as one causing the other. We don't want to do that. All correlation is saying that they are connected in some way. We don't know if it's direct, which direction, or via some third variable that we might not realize. Okay, so that is one very important thing. The other is, if I think about this before I show that slide, I'm so tempted for that slide. Let's just think about this. What we have here in our first example is a sample from the underlying population of people with loneliness scores and depression scores. There are many, many more dots. These are just a sample of 6 of those. And if you take a different sample, you'll get a different correlation coefficient. So this correlation coefficient is really a statistic. It's an approximation of the true population correlation coefficient. So this approximates the population correlation coefficient, which we'll call rho. Oops, I can't see that. Move it a little bit. Just like any other sample, it estimates something about the underlying larger population. And there is natural variation in my small sample. So we can't say that depression and loneliness are related with the correlation of 0.73. However, we want to interpret it with R squared or not. It's an approximation. And because of that, we need to test how strong this evidence is in terms of its representation, its estimation of the true underlying population. So we have a test for the significance of this. Now, luckily, there's good news and bad news. The bad news is it's a new formula. The good news is that this follows a t-distribution again. If we calculate this guy, this follows a t-distribution with the degrees of freedom, the sample size -2, because I have 2 columns, so I can take 1 away on each side. So n -2. So for our example here, we would have degree of freedom 6 minus 2, so 4. I think I'm on this slide. Yes. So we can't take the correlation coefficient as perfect. It is a sample value and therefore an approximation of the population. So what it gives us evidence. We don't know necessarily how strong that evidence is. So before I show the examples, what we're testing here is our null hypothesis that the population, let's say the correlation between the populations, those two populations, is 0 versus, oops, it is not 0. And we're asking, is the evidence in our correlation coefficient R, is it strong enough to suggest that the correlation, the true correlation, is not 0? That these variables are in fact related to each other. Remember, a 0 correlation means they are not related in any way. And the higher I go to 1, the stronger the correlation is. So if I look at my loneliness and depression example, we got our 0.73, if you remember. And again, we'll do this in more detail in upcoming videos. Right now, these calculations are all done for you. 0.73, and we had 6 people in our survey. This is the hypothesis test that we are conducting. Our t-score, let's say t observed, we calculate, plug the correlation coefficient in there, the group size, so on. Our degree of freedom, we said degrees of freedom 4. Our t cutoff is what we need to find. So let's go to our t-table here. It's a two-tailed test. Oops, I did not specify. Let's take an alpha of 0.05. What is our t cutoff value? Well, it's a two-tailed test. Alpha 0.05, degrees of freedom 4, 2.776. 2.776. We compare that to the 2.15 that we got. Don't want to show the next one. Just want to squeeze it in here. And what is our conclusion? Our conclusion is this does not sit past the cutoff. It's not greater. So the evidence is not strong enough to suggest that there is a correlation between these two. So we cannot reject the null hypothesis. The evidence is not strong enough to suggest that there is a correlation. Now, there might be one. We had a small sample, and that sort of plays a role in here. Because small sample, you have a lot more variation, so you could get something that in that sample has a seemingly strong correlation. But as far as the population goes, the evidence cannot be trusted that that's actually true for the whole population. So it's something that people struggle with a little bit, like, oh, I got a 0.73. How is that not a strong correlation? We're ultimately trying to say something about the population. And a small sample has a lot of variation. I could get my next sample of 6 people could have 0.01 for a correlation. So the question is, how much can I trust the evidence to accurately reflect what's happening with the populations, and if those variables across all people actually have a correlation? So that's why the test for significance is very important. Let's do another one. Let's move that up like this, over here maybe. Love and conflict. We did that over here, right? No, over here. Yes. And we found we had 7 people, correlation coefficient of negative 0.64. It's over here, 7 people, so our degrees of freedom will be 5. Our observed t-score is calculated to be 1.88. For an alpha of 5%, we get our t cutoff as 5% over here, degrees of freedom 5, 2.571. 2.571, and you see again, it's not even close to the cutoff line. We cannot trust this evidence and say, oh, that for the population of these two variables, it is correlated. Maybe, maybe not. The evidence isn't strong enough. We cannot reject the null hypothesis, and we can say more here. The evidence is not strong enough to suggest a correlation. What can we do then? Well, we can increase the sample size. Larger sample, and we'll know much more. But because we're doing it by hand, we're a little limited here. We can't do this for a large sample. So we're kind of at the mercy of that because we're doing it by hand, but a larger sample and the evidence would definitely point out if there is a correlation, it'll show it. Small sample, and I have a lot of variation that I can't necessarily trust. Okay. So again, those two things are, well, okay, so there are 3 things that are important. 1, how do I calculate it? How do I calculate the correlation coefficient, and how do I interpret that? It is, however, a sample correlation coefficient that only estimates the population correlation coefficient. And so it needs to be tested for significance. Can I trust that? Can I trust that sample correlation coefficient? Is it strong enough evidence? A t-distribution. Luckily, it's not a new distribution, so that's good. And then lastly, just because even if the test says, yes, it's significant, it still does not mean that one causes the other. And in some cases, I'll never know which causes which one. Does one directly cause the other one? Which way? Is there a third variable I'm not realizing? Those are really hard to really identify. But knowing there is a correlation is still a lot of beneficial information. All right, so that wraps up our short and sweet introduction on correlation. This will roll over very nicely into our next topic, and these really, I do see them as one thing, but they're split up separately to keep things nice and manageable. But we will continue this in the next video. Until then.